Yes, that's actually a point I'd really like to make as well. So, first of all, thank you, Svenja, and for the organisers for having me here today. I'm really excited about this framework that I built, and I think it's something that's going to be readily applicable to a lot of your work as well. And really, it is a way to link histology and macro-scale understandings of the cortical organisation. This is being difficult. Here we go. Okay, so traditionally, histological studies have delineated areas of the cortex according to their cytoarchitecture and myeloarchitecture. And then we've built this together in vivo modeling to look at their similarity and connectivity, and we get a more systems level understanding of cortical organization. And as we've fused these fields together, we've started to understand this hierarchical organization of the cortex, where you start off with the sensory areas at the lowest order, where the information seems very detailed, and you have this laminar structure that's these 6 clear layers. As you move up and the information flows up to the limbic areas, the lamina is less differentiated, becomes dysgranular. And what I've wanted to see if we could look at this in a systematic way using the microstructure and somehow link these histological fields and these more systems levels understandings. So to start off with, I started looking at the big brain data, which a few of you would have seen talks on today. It's this really amazing data set that came out of a collaboration between ULISH and the MNI. I'd like to thank the researchers for making that publicly available, by the way. And it involves a 3D histological reconstruction of a single postmortem human brain. And there's some really cool work coming out that's using this to make new atlases, and as Conrad spoke about, looking at the manual segmentation of the laminar as well. But I want to take this more systems level approach to this. So to do so, I decided to build a new framework called Microstructural Profile Covariance. So I downloaded the 100 micron resolution big brain data to start off with, as well as the peel and white matter surfaces, which you can see presented here. Then I generated a number of surfaces between the outer and inner cortical surfaces. Then at 80,000 vertices across the brain, I sampled the intensities at all these surfaces. So you have an intensity profile for each vertex. When you put these all together, you end up with this whole cortex vertex-wise profiles. And the intensities here give us an understanding of the cellular density throughout the cortex. Then I decided to make a similarity matrix out of this. So I used a partial correlation between each of the nodes. So I compiled all these 80,000 vertices into 1,014 nodes and performed this partial correlation correcting for the mean intensity at each surface. And the hot colors here represent greater similarity between the nodes. So I noticed something really interesting as soon as I just started looking at a few seed regions, as we do. And if you look on the left of the screen, you see some sensory regions. I saw that these always tended to co-vary with other sensory regions as well as prefrontal areas. Whereas when I was seeding from transmodal areas, it seemed like it was this other network between the cingulate and the insular and temporal lobe areas. So I wanted to investigate this in a more systematic way. And then as Xavier just presented, I use this gradient approach, which means we use diffusion embedding, which is a dimensionality reduction technique. It's a nonlinear principal component analysis. So we take this first matrix, which shows the similarity between nodes based on their microstructural profiles. Then we convert this and sort it according to nodes which map onto similar nodes. So nodes that are close to each other on the gradient map onto and covary with similar nodes, and the ones at the opposite ends of the gradient have very dissimilar covariance. When we project this back onto the cortex, you see these two networks emerge again. At the low end of the gradient, you see these sensory areas and prefrontal areas, and then at the top end of the gradient, you see these cingulate, insular, and more transmodal areas. And what I found really striking was it reminded me of this beautiful atlas made by Meselem from 1985, which shows laminar differentiation. He delineated in blue there is the idiotypic primary areas, which have this very clear 6-layer structure. Then you have the association areas in pink and yellow, and then right at the top are these paralimbic areas, which are more dysgranular. And when you look at the placement of these classes on the gradient, you see this really clear effect. So I had to actually manually assign each of the nodes to this atlas, and you see that the idiotypic areas really lie at the bottom of the gradient. Then you have the association areas in the middle, and right at the top you see these paralimbic areas. So it seems like we're sensitive to laminar differentiation here. I think the evidence really supports this seminal literature on the relationship between cortical hierarchy and laminar differentiation. Then with ongoing work, I wanted to see if we could translate this to in vivo as well. And to start off with, I used the Human Connectome Project data, which I'm sure all of you are well acquainted with. I started off by just using 110 subjects, and specifically the T1 over T2 weighted images. I chose that because it's sensitive to myelin, and we do know from histological studies that cytoarchitectonic and myeloarchitecture boundaries seem to overlap. And also T1 over T2 weighted images are available in a lot of these large-scale data sets. So I thought it was a good starting point at least, and we can look into looking at more quantitative measures in the future, I think. So in the exact same manner as what I did with the big brain data, I went through this pipeline. I started off with the peel and white matter surfaces, generated a number of surfaces in between. Then at each vertex, in this case there was just 20,000 vertices, I sampled the intensities. From that, parcellated into nodes, constructed a similarity matrix, and then applied diffusion embedding to get this gradient at the end. So this gradient is representing the microstructure profile covariance in vivo data. Here I'm just showing a group level analysis, but I'm also working on individual analyses at the moment as well. And already it seemed like there were some similarities to the histological data, and you see it is significantly correlated with a rho value of 0.27, and this was really driven by the similarity at the very bottom of the gradient and the very top of the gradient. So sensory areas are the bottom of the gradient in both cases, and those transmodal areas are at the top of both gradients as well. Then for those of you who are familiar with Daniel Margulis's paper, which really started this diffusion embedding craze, you'll see there's some similarities there as well. And indeed, when we correlated the two, you see the rho value of 0.54. So it's also sensitive to the functional gradient. So we're really trying to bridge this gap in between the histology and the function as well. And that's why we also looked at the placement of functional communities along the gradient. So I looked at the Yeo and Creenan communities. You see at the bottom of the gradient are these sensory motor and visual areas. You move up through the attention networks and frontoparietal networks. And then right at the top of the gradient are the default mode and limbic networks. So just to pull this over together, I hope you think this is a really useful framework. I think it can complement a lot of macro-scale analyses as well. So it might give us a more nuanced view. And I think this is really working towards this multi-level brain organization understanding, which Katrina Muntz gave a really wonderful talk on this morning, how we really need to start looking at brain organization across many scales as well. I thought the microstructure in particular seemed to be something we were struggling to bridge this gap with. Also, I think that because it looks like the functional gradient, things like that, if we start looking at individual levels, individual gradients, we maybe can relate this to individual characteristics and look at aberrations in different psychological and neurological disorders. And finally, I'm personally really interested in neurodevelopment. So I'm going to start using this data to look at the principles that guide microstructural development and see if we can gain some more understanding by using this microstructural profile covariance. And finally, I'd just like to thank my wonderful lab, the MICA group at the M&I, and especially my professor, Boris Bernhardt. And also, there's been a great group of people at the M&I who have helped out. And definitely a huge thank you has to go to those big brain and HCP data sets. Without them, this would not be possible at all. So thank you for your attention, and any questions? Thanks.